everyone. Welcome back to SAT Math Question of the Day with Professor Brothers Chaiken and Seth's brother Joel. We're here to hopefully show you how to approach studying for the math SAT and also how to approach actual SAT math questions. In terms of studying for the SAT, it's a great way to do it. It's completely free. Is go to Khan Academy. You can see how to do this on our video dated June 29th, 2023. Where we show you exactly how to find SAT practice for the digital SAT, which is going to be given in the United States starting in the winter of 2024. So that being said, we just plow through these problems. We're going to be here for many days going through these problems. So today we are at advanced problem solving. We're only doing the advanced problems, with the presumption that if we hopefully explain, how the advanced level works, then you can go ahead and do the lower two levels. So yesterday we did data representations. Today we're going to start a new topic, scatter plots advanced. So scatter plots is generally mostly common sense, similar to yesterday's question. And let's go. Okay, here we have I think there we have the entire question. Yes, the entire question is on the video. Okay, please everyone read it. Pause, come back, and we'll do it. Okay, the plot in the DI plane shows the light intensity I in watts per square meter. Good, the units are there. At a depth d meters below the surface. They also could have said as a function of d. As a function of the depth, which of the following equations best models the relationship between I and D? So they're looking for a functional relationship based on the graph. So
okay, well, you know what? Here's an approach to this problem.
Go ahead.
That I'll summarize first.
Good.
My eyes looked at the answers.
Oops.
And then they looked at the curve.
Right.
Okay, whoops, sorry. Yeah. The curve goes like this. The curve goes like this.
Yep.
Okay, and this is, okay. Now, I looked at the answers, looked at the curve, and I see the answers all had the form some exponent, A to the plus or minus d times some positive constant with a plus or minus.
Right.
All right, so what could it be? This one, it's a positive coefficient and a positive exponent, so it's rising.
Yep.
Not that.
Right.
Here, a negative coefficient and a positive exponent. So it starts out a little negative and then falls.
No, it doesn't. No, it doesn't fall. Oh,
it starts out a little negative. Yes, it does.
Which one are you doing?
It's negative. It's negative.
Seth, which one are you doing? Oh,
B.
yes, it falls. Right.
Yeah.
Yes, right. You're right.
C starts out positive, and it non-zero positive, like that. Yeah. So, and this one, it starts out negative, right? And it rises to zero. So it has to be C.
It has to be C.
And in fact, the way I saw it was, I looked at the curve and I saw this is the only one with a negative D, and a positive C.
Yep.
Immediately, that's the curve. That's the shape.
Right. Yeah.
Move on to the next question. Obvious.
Seth, come on. Don't be obnoxious.
No. So when you're taking the SAT, you're ready for this kind of question when you could do that.
Yes. That's a good way to know. That's a good way to know when you're practicing, when you're a good approach to studying is when you can do a problem like this almost immediately, then that is a good sign.
Okay. Well, it's always no. It's not such a good sign because it it's a sign that you don't have anything to learn at this point. So you're not learning anything. You're just confirming that if you run into a question like this on the SAT, you'll be able to do it.
Yeah.
But it's not making progress in learning something new.
True.
So I think so. What is it? We should now turn the page to help people to understand who don't understand what's happening, and therefore for whom this question is something they can learn from.
Okay, I agree. We'll do another question today, but I just want to make a comment as to sort of how I would have done it. Although I think it's the same way as Seth. I would have known. First of all, I would have looked at all the answers, and I would have seen they're all exponential functions. The function is going down, so the exponent's got to be negative. So,
No, if the sign of the constant is negative and the exponent is negative, it goes up.
Okay, fine. So then let me say, if you have a first quadrant, if you have an
there you go. First quadrant.
if you have a
first
graph
quadrant,
that's in the first quadrant,
which this is,
and it's going down,
positive.
Right. Okay, Seth.
Positive.
Okay, yeah. If you're in the first quadrant, you have a graph going down. That means that the exponent's got to be negative. So you cross these two off.
Yeah.
And it's got a positive y-intercept because it starts here. The only one with a positive y-intercept.
No. If it's in the top quadrant,
then it already has
it will always have a positive y-intercept.
I know.
Yes, it is. What are you?
But it's okay. It's okay to double think. It's fine. Anyway,
it's much better to single think.
Sad. But people,
the thing about the thing is that's important to know about exponentials is that CA was it to the D, CA to the X?
Yeah,
right?
CA to the X. Yeah.
Okay. First of all, when X equals 0, this thing equals CA to the 0, and any positive exponent to the 0 is 1. So it's always, now so if C is positive, the exponential curve starts up here.
Right.
If C is positive, and it starts down here if C is negative.
Right.
Okay. Even though, and okay, now X, here's X. But let's see, let's make the exponents plus or minus. Whether or not, whether it's the exponents is plus or minus, it doesn't matter. The 0 point is always on the 0 point is always the value of C.
That's right.
Right?
Right.
So now, given that, if the sign of the exponent is positive, the absolute value of the function, the absolute value of the function, the thing is we have to also know about exponentials, is that, for a positive exponent, the sign of this, the value of the exponential, when you have a positive exponent, is always greater than 0.
Yeah, but a to the negative. Wait.
Always greater than 0.
Yeah, but even if X is
okay, so let's see the difference. A is positive. A is positive. It starts at here. The coefficient is 1 when the exponent. Sorry, when the constant multiplying the exponent is positive, what we have is exponential growth. Exponential growth. Right?
Right.
So this is a to the cx when the exponent constant is positive. A to the minus cx. Again, c is greater than 0, so minus c less than 0. Then you have exponential decay. It starts out this way and then becomes asymptotic to 0.
Right.
Right?
Yeah. Yeah.
Okay.
Right. Okay.
Okay.
And then when a is less than when you're below the axis, when you're down here, like -3 2 to the 5th.
Yeah.
Right. Then that simply goes. Oh, that's a big negative. That means whoa, it keeps getting big negative because 2 to the 5th
value
becomes
negative.
minus. So that becomes that.
Yeah.
And then let's just switch colors. And then -3 2 to the -5. This number gets small.
Yeah.
Absolute value. So this one becomes here and goes like this, and it goes like that.
Yeah. Okay. So I think an approach to learning something from this question is to by yourself make up a reminder note about actually the answer distractors. The distractors give all the 4 possibilities. The combination of positive or negative for the multiplicative constant and positive exponent and positive or negative for the exponent. The base of the exponential is common, 1.65, and the two cases are plus or minus d. So here the 4 cases are plus or minus some number. Let's say in between that, about 1,000. No, about what was it? Maybe about 1,300. Plus or minus 1,300 times 1 and 65/100.
So why don't you just look
times plus or minus d. So we have plus minus plus and minus.
So look, I just put A, B, C, D. I just
labeled which or which. This is plus. This is plus minus. This is minus plus, and this is minus.
Yeah, so instead of memorizing this plus minus stuff drives you crazy, just make sure you know that these are the 4 possible ways, and this is what the graphs look like, and you should make a little cheat sheet. People highly suggested to make a cheat sheet which goes over this, and then you understand it.
Yeah. Well, another systematic. Let's do another systematically. Let's draw a line between the cases of the sign of the coefficient. Now imagine a mirror. Is a mirror.
Yeah, right.
You take this, flip it over. Take this curve, flip it over. Take this curve, flip it over. Flip it over.
Right. Yeah, you get that.
Right?
Yeah.
And this one, and flip it over, you get that.
Right.
Right?
Yeah.
Well, flipping it over is akin to turning the y-axis over.
Right.
Right?
Yeah, that's called the transformations of functions. If you put a negative sign in front of the function, it flips it across the x-axis. It makes whatever positive
Yeah.
with y, it makes a negative one. Yeah.
Yeah.
That's the whole
Yeah.
thing about
Yeah.
transformations of functions. That's a
Yeah.
good insight. That's a good insight.
Yeah. And then, you could make a corresponding argument about the sign of the exponent. However, uh, however, what that entails dealing with curves in which the independent variable might be negative. Well, thing is that what's the whole picture? The whole picture, the case A. The whole picture for case A, which is plus times plus to the plus x. The whole picture is exponential growth up here, but but exponential decay as x becomes more and more negative.
Yeah, okay, but let's not get
And then if you flip this around, if you flip this around,
right, you flip it around the y-axis.
Yeah, you do a mirror flip around the y-axis, you get this case.
Right.
Yeah. That's because what Joel did not draw is the negative side.
That's true.
Of that. And
yeah,
he didn't
so
draw
this
the
does bring in
that
idea of transformations of functions, which is important.
Yeah.
It's not clear whether the SAT does that stuff, transformations of functions. It's possible. We'll find out.
Well, when you know the whole picture, it's easier to remember it because more of the properties are related to each other.
Right. Yeah. So that's basically saying that for the entire function that goes like this, for growth, it goes like this, includes the negative sign, and starts to grow like that.
Yeah.
And then if you flip it across the y-axis, then it's really decay, and it goes like that. Wait. Let me just do it.
Yeah, you flip it across the y-axis, which means you change the sign of the SIGN.
Right. So this is
the x-axis.
This is 3.
Yeah.
This is 3 to the negative x, and this is 3 to the x. See, when you change the x to be negative, it flips things across the y-axis. Do you see that?
Yeah.
See everyone? See how it works. So let's see how they do it. Let's see that we certainly gave more than one approach on this. Remember which one it was again? It was this one. Okay. Let's see what they do. See how we answer this question. Okay, let's do that. There's the graph. The plot appears to be always decreasing and always at least 0. Okay. The rate of decrease is also higher for smaller values of d. These are properties of an exponential decay. We can fit a curve to the data as shown below. There's the data. That's what Seth sort of implied. He actually wrote something similar to that, step 2. And then it said here that the I-intercept is greater than 1,000, A has to be greater than 1,000, and D has to be, A is a positive constant representing the, what? A must be a positive constant.
Yeah.
K must be negative. K must be negative to represent an exponential decay.
Okay. Now, there's something this leads me to realize I omitted a very I omitted emphasizing a very important point about that last problem.
Yeah, and I think
When we talked about these four cases, right?
Yeah.
What were the four cases? The
Yeah.
four cases were.
I think I know what Seth's going to say.
Exponential.
Yeah.
Growth.
Right.
Exponential decay from a positive. Exponential.
Yeah. The four cases.
Growth in the negative direction, and exponential decay.
Right.
In the negative direction. With all of them, the exponent, the base. B is the base of the exponential. The base of the exponential is greater than 1.
Right.
If you had a B now, so to consider when B is less than 1,
yeah,
this is equivalent to using, instead of B, the opposite sign of B, which is greater than 1. So indeed, so we have B to the X.
No, you're talking about the X, Seth. The X changes sign, not the B.
No. The B. The B, if B is a number, if B were a positive number less than 1.
Yeah, it'll be a fraction.
They put it in parentheses.
Yeah, it'll be a fraction.
Yeah, if B is a fraction,
a proper
fraction less than 1.
If B is a positive fraction, a regular
positive
fraction. Normal
fraction, proper fraction,
right,
which is greater than 1. You could have a No. Improper fraction is greater than 1.
Just a normal fraction, like 3/10 or something.
If B were 3/10, it would be a fraction less than 1.
That's right.
And B to the positive X would give you negative growth.
That's right.
Right. And so, indeed, the thing is, if B were, this is, by the laws of exponential, this is the same as 1 over B to the minus X.
That's right. That's right. So
here B is greater than 1. And let's use blue. We'd have this situation. Let's see what we have. We have this situation.
There's a problem. Wait, hold on.
We have this situation when B is less than 1, and of course greater than 0.
Wait a second. 1 over B to the X is the same as B to the minus X. That's a better way of thinking about it. This is a better way of thinking about it. I don't know. This is confusing. If you have 3/10 to the X,
you could replace this B by 1 over B.
Yeah.
It's equivalent.
Right. Yeah. No. But I think this gets to the heart of the matter better. If you have 1/3 to the X, that's equivalent to 3 to the negative X.
Yeah.
Right. So you can always take a fractional B and turn it. When I say fractional B, I mean a fractional B between 0 and 1.
Okay, so how do you remember? What's the sense of this? What's the sense? With positive B.
No, forget positive B.
I'm sorry. If for B greater than 1.
For B greater
what you
than
have would B is the base. B is greater than 1. We have 1 plus something extra. And then when you raise it to an exponential, right? If you square it, what you get is the same 1 plus 2 times the positive plus the positive squared. You multiply it by but again, let's say if this is greater than 1, like 1 1/4.
Right.
So 1 1/4. This is greater than 1. If you multiply it by itself, another greater than 1, it grows more It grows.
It grows.
Because
it
you're
grows.
multiplying a number bigger than 1 by another number that's bigger than 1.
It grows.
So you have a number that's bigger than both of them.
Yes, we said that. It grows.
And you keep multiplying. It gets bigger and 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 boom.
Right, that's right.
Exponential growth.
That's right.
Now, what if you have a number less than 1? Like a half.
Then you take
half. Yeah, half a loaf. It's not too big. Not too small, not too big. Take half of half a loaf.
Right, get smaller.
And you get only a quarter loaf.
Right.
And then take another half. Horrible. Another half of your quarter loaf. And you get an eighth of a loaf.
It gets smaller. It's called
and then take a half of that.
Okay,
yeah.
Get the point.
And a half 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 and a half. Get really, 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 really tiny.
Then you're left with nothing.
Almost nothing.
Yeah.
But you never get to 0.
Yeah, but in terms of measuring it, you could get to a point where there will be no device on Earth that can measure the difference between what you have and 0.
But it's still not 0.
It's still not 0. But in practice, for all practical purposes, it's 0. For all practical purposes, it's 0. So
that's
so
still not 0.
The base.
That's what the mathematical. That's what mathematical thinking is about. Even if, no matter how small it is, if it's non-zero, there's a logical difference between something being 0 and non-zero.
Absolutely.
No matter how small it is.
That's absolutely right. Absolutely right.
And the thing is, if it's extremely small, you could multiply it by a huge number.
Yeah.
And get a reasonable size number.
That's right.
But if it's 0, exactly 0, no matter what you multiply it by, you get 0.
Right. Yeah. Okay, boy. So I don't think we need to go over another. We already used up.
We covered everything here.
We covered everything here. But yeah. So yeah, be aware that when the base, it matters what the base meaning the thing that you raise to the exponent. It matters whether it's a number between not including 0 and not including 1, right? Yeah, that's okay if it's a positive exponent. As long as positive exponent, and then if that b is greater than 1, then it is a growth.
Okay, what happens if the base b is equal to 1?
That just stays constant, because 1 to any power is always 1.
Why?
Why? Because if you can multiply 1 as many times as you want, and you'll always end up with 1. 1 times 1 times 1 times 1 times 1, no matter how many 1s there are, there's always 1. And that's
okay, what if you start with 2, and you multiply that by 1?
What are you talking about?
It's not just 1 multiplied by 1 doesn't give 1, but if you start with 2 and you multiply it by 1, what do you get?
Wait. If you're talking about y is equal to 2 to the 1 to the 30th power, or to the x power.
Right.
Well, then it's always 2. It's always 2. Because this
starts
1
at 2.
to the x, this 1 to the x is always 1, no matter what x is. And even if
but
x is negative.
also, so you're talking about distributing it this way: 2 times 1 to the x.
Yeah.
But you could also talk about it this way: 2 times 1 times additional 1s. So you start with a 2, multiply it by 1, you get 2.
Yeah.
Multiply it by another 1.
You get 2.
This is 2.
Yeah.
The 2 times 1 doesn't change. It's still 2 because anything multiplied by 1 is itself.
Right. Yeah.
You have a bear.
Yeah. You have a bear?
A bear, yeah. Multiplied by 1.
Yeah.
And what you have is 1 bear.
Yeah, 1 bear, right. Yeah.
Yeah.
Yeah. Okay, I think we've done more than enough. Let's clear this. Okay,
Okay.
everyone, have a great day. Please like us, dislike
So
us.
this is what I want to say is a good way to approach studying exponentials for the SAT. To make up stories and have fun with it, with all the variations of multiple multiplication, because exponentiation is multiple multiplication, with a rule pertaining to negative exponents, take the reciprocal, and non-integer exponents, which means kind of a partial multiplication, like multiplying uh uh multiplying t b to the 1/2 multiplies it partially through to 1. It multiplies it in such a way that if you multiplied it by b to the 1/2 again, you get it multiplied by b.
Yeah, we're not talking about that.
So okay, so again, what's fun is to look at all the four possibilities, make up fun things, like if you start with a bear and multiply it by 2, what happens? Start with a bear and multiply it by uh multiply it by uh a half, get half a bear,
So what
and do
are
it
you
again and again and
talking
again.
about? Look, most people watching this will have lived through COVID. And COVID's the classic example of exponential growth and decay. COVID, maybe one person had COVID, and then, whoa, look at that, exponential growth. And then after everyone's got COVID, whoa, exponential
Yeah.
decay, growth. And people know, hopefully, it's likely that most people watching the video will have seen the charts and lived through exponential growth with COVID-19 and then exponential decay, COVID-19. And that's always a good thing. When you
But how
live through.
about, but this also goes up and down.
Yes, I know, but this is just old. This is only went on its major growth spurts because there were periods of COVID where things just went
Yeah.
exponentially high, like with Omicron, and then
Yeah,
decay.
yeah.
Basically, everyone had Omicron.
Okay, why is the initial behavior growth of an epidemic exponential?
Because you're giving it to one person, gives it to more 3 people, and then those 3 people give it to 3 other people, and then now you've got like not 9 people, and then those 9 people give it to 3 other people, so you have 27 people giving it to 3 other people, and then you end up with every person gives it to a bunch of other people, and that's how you get exponential growth.
Yeah, why does it level off?
Because eventually everyone has gotten sick, or
Yeah,
people have built up immunity, so it levels off. Yeah, you've run
yeah,
out.
yeah.
You
It
just run
starts.
out.
It starts. That's each person. If there's so many people with COVID around, one more person with COVID doesn't give it the first time to the same number of people. So one
Right.
person with a lot of people around, he transmits the COVID to maybe 3 people, but already 2 of them already have it. There's
Right.
only one new person.
Right. Exactly. Yeah. So it levels off. Yeah. Yeah.
Yeah.
Okay.
Okay.
Oh, well, wait. One other thing that we completely ignored. Why did we completely ignore it? Because frankly, it has nothing to do with the problem, but they make a big deal about it. We're so smart here. We're doing functions. It turns out this is not a. This function is only a model. This is a scatter plot. This is not a clean function.
Oh yeah.
This is only a
Oh yeah.
scatter
Right.
plot. So frankly, we completely ignored that. And
Oh, we
frankly,
forgot
like,
that part.
who
Yeah.
cares? Who cares? Now
The model.
in the answer they mention best models the relationship. But come
Yeah.
on, I mean, all of these 4 are so
Oh yeah.
different from each other then it doesn't matter whether it's a stupid scatter plot or not. We just treated it as a function, which technically Seth talked theoretically, the difference between a number that's basically 0 and not 0. We made a conceptual mistake here, but frankly, who cares? And it really doesn't.
Yeah. Yeah. Well, look at the plotter. It's
close enough.
It's close enough, but it's visible that's not quite smooth. So this point looks. Don't move it around, please.
Sorry.
I'll don't move it around anymore. This point, don't move it around, please. I said no. You still did. Okay, here we go. This point here looks a little bit high. This is a little bit high for it to fit on a on a curve, on a smooth curve, and this one is a little bit low.
Yeah. Well, you can.
So the dots represent measurements, which are or outcomes that don't fit the model exactly.
Yeah, you could see that that's here, right?
Yeah.
You could see.
So the question was which formula is the best model for the observations shown on the scatter plot?
That's right. So whenever you're talking about all this statistical stuff, the question is there's always a best thing in there. What's the best thing, not the exact thing? Again, in this question, we completely ignored it. We spent more than 30 minutes on this. We completely ignored that, and frankly, it really didn't make a difference.
Yeah. However, the question did not ask about, did not address or deal with the issue of differences between models and data.
That's right. And that's right.
The question was, given a curve whose qualitative shape is sketched by those dots.
Right.
What's the best formula or the formula that could be that curve?
Right, exactly.
That's the heart of the question, and that's why it worked to simply address it that way. Okay, exponential function.
Yeah. Okay,
which case is it? It's a case of positive.
Yeah, we know.
Multiplicative coefficient, negative.
Decay. Just say
exponential coefficients and greater than 1 exponential base. Bingo. Pick the choice. Right. Go on to the next question.
Right. Okay, enough. We're done. 38 minutes.
Okay,
we spent too much time on this crazy question.
Done, hon.
Okay, so everyone, again, now we end. Okay, please email, like us, dislike us, particularly tell us if we're too crazy. Leave comments on our YouTube videos, or email us your SAT math questions at satmathquestionoftheday@gmail.com, and we hope to see you tomorrow. Take care. Bye-bye.